Have you ever looked up at a massive skyscraper and just wondered, how? How does that thing stay up? Or a bridge, with thousands of cars streaming across it every single day? Well, today, we're pulling back the curtain on the invisible science that holds our world together. This is all about engineering mechanics.
It really all comes down to a single gigantic question. How does an engineer design a bridge and really know that it's safe? How can they possibly predict how every single piece of steel is going to react under all that stress?
The answer isn't just crossing their fingers and hoping for the best. Nope. It's a whole field of science that gives them the tools to see into the future of a structure. And it all begins with one single fundamental idea.
That's it. At the heart of everything, from the chair you're sitting on to the most complex airplane engine, it's all about forces. You know, the pushes, the pulls, the twists. Understanding how those forces act on an object is the absolute key.
So, to actually calculate all those pushes and pulls, engineers need an essential toolkit. And that toolkit has a name.
It's called mechanics. And yeah, it's a branch of physics, but don't let that scare you. All it really means is that it's completely obsessed with one question. What happens to a thing when a force acts on it? Doesn't matter if it's a book just sitting there or a satellite zipping through space, mechanics has the answers.
And this is where it gets really awesome. Engineering mechanics is what connects that pure physics theory to, actually building stuff. It takes all those core principles and puts them to work solving actual, real-world design challenges.
Now, mechanics is a pretty big field, so we usually split it into two main camps. You've got the mechanics of fluids. Think about water pressure behind a dam or the fluid in your car's brake lines. Then there's the mechanics of solids. This is the stuff our world is literally built on: steel beams, concrete pillars, machine parts, and that is going to be our focus today.
Okay, so you might be thinking, this sounds insanely complicated. And honestly, you're not wrong. But engineers have this brilliant trick up their sleeve. A little simplification that makes the math go from impossible to totally manageable.
But hang on a second. We all know that things in the real world bend. They stretch, they compress. If you put enough books on a shelf, you can see it sag. So how can engineers do any math if the very thing they're measuring is changing shape?
This is where that clever trick comes in. In reality, a 200mm steel beam under a heavy load might actually compress to, say, 199.99 millimeters. That tiny, tiny change makes the math a nightmare, so engineers create a model. They just assume the beam is a rigid body, that it doesn't change shape at all. And suddenly, the calculations become way, way simpler.
And here's the truly brilliant part. Because that real-world change is so incredibly small, pretending it doesn't happen introduces almost no error into the calculations. We're talking fractions of a percent. It's a tiny white lie, but it's the lie that makes designing pretty much everything possible.
All right, so we're dealing with solid, rigid objects. From here, we can split the field into two major buckets based on one really simple question. Is the thing moving, or is it just sitting there?
First up, you have statics. Think static, stationary. This is the entire world of things that are at rest and are supposed to stay at rest. We're talking buildings, bridges, dams, all that good stuff. Then you've got dynamics, and that's the complete opposite. It's the study of things in motion. Think about a moving car, a satellite orbiting the Earth, or even just a football flying through the air.
But we can actually get even more specific with dynamics. We can ask another question. Are we just trying to describe the motion itself, or do we care about what caused the motion in the first place?
And that question splits dynamics into two little subfields. First, there's kinematics. This is all about the geometry of the motion. How fast, how far, how high. It answers the question, how high will the ball go? It doesn't care why. Then you have kinetics. Kinetics connects the dots. It looks at the motion and the forces that caused it. It asks, okay, but what kind of force did it take to get the ball that high?
So when you put all these pieces together, statics, dynamics, kinematics, kinetics, you start to see that engineering mechanics isn't just a class you take. It's the fundamental language that engineers use to design and build our entire world. So let's just do a quick recap. Mechanics is the science of forces. To make the math work, engineers use a clever simplification called the rigid body model. If something's not moving, that's statics. If it is moving, that's dynamics. And really, this is the invisible science that's holding up pretty much every single physical object you use every single day.
So the next time you cross a bridge, or even just lean back in your chair, take a second. Think about those hidden forces, all perfectly balanced. What invisible science do you see holding it all together?